Chapter 3. Chapter 3 is on applications of differentiation. So all that derivative rules, everything we just learned, we're getting a little more applied into different things, different scenarios. We talked about those related rates thing. That was one example of that. These next things, we're looking at different ways to apply them, kind of similar situations. They will not be as rough as related rates were. But our first one here, we're going into an extrema of an interval. So in calculus, much effort is devoted to determine the behavior of a function f on an interval, and doesn't have a maximum value, doesn't have a minimum value. Is it increasing? Is it decreasing? Those are all important questions for us to answer in different functions. And especially when we're in a real life scenario, you get the classic problem of, think back to quadratics. When you throw a ball up in the air, at what point does it reach its peak and then start falling back down? Okay, we had critical points of the max. We found the min was when it returned back to Earth at our x-intercept, those types of things. We can do the same type of thing, but we do it on recurring functions. We can do it on curved functions that are beyond a quadratic function. So just by definition, we have what's extrema. Extrema is going to be your minimum and maximum on certain intervals. Okay, it might not be over the entire thing. It could just be on an interval. During that interval, your max on that might not be the overall max of the function, but we're only looking at specific intervals at different times. Okay, extreme value theorem. I think we talked about this once before. If it's continuous on a closed interval, then you have to have a minimum and a maximum in that interval. There's no matter what. Even if it's a straight line, your minimum and maximum are still going to be the same point there. Definition of relative extrema. There's an open interval. There's a maximum. We call that, it's called your relative max, or you can say you have a relative min. That is going to be the largest one kind of in that group. All right, so for instance, if I draw this picture, something like this. All right, if that is the entire interval, this is our max point here. Agreed? It's the highest point we got. This would be our minimum. Okay? This would be a relative min. This would be a relative max, because it's the biggest and smallest in that area around it. Does that make sense? So you have an overall max, and then you have other maxes and mins within that points. Okay, those are relative ones. Or you sometimes call them local max and local mins. I'm going to be honest with you. I'm probably going to call it local max and local min more so myself. That's just the way I was taught, but I wanted the wording to be the same as the book. Okay, so if I'm talking about a local max or a local min, it's the same as a relative max. So back to our picture. This is an overall max, overall min. This would be a local min and a local max. You with me so far? Okay. All right, so let's just look at a couple. Find the value of the derivative at each relative extreme function, or extremum. I can't say that word, shown. All right, so I have three pictures there on the side. The very first one, we're going to look at, I'm going to tell you that the max is at 3, 2. Okay, that's my max. I want to find the value of the function at that max point. And the function that is shown, I just took a snippet of it. I just zoomed in on a certain area of the graph. This is the function f of x was 9x squared minus 3 over x to the third. Now, as we're going through these today, when we find the derivatives of stuff, I might not do a step by step by step. All right, we've done enough derivatives. You can find the derivative and simplify it. You know what I mean? So a lot of these I'll probably do like the first step and then skip to like the last step. You with me? Just for the sake of time. All right, so that's the function. 9 times x squared minus 3 over x to the third. So first off, let's find our f prime of x. So we want to find the value of the derivative at that point. So f prime of x, oh, it looks like I'm going to have low d high. It's x to the third, 18x minus 9, x squared minus 3 times 3x squared. That would be the quotient rule and u substitution. That's all going to be over x to the third x squared. Okay, so low d high minus high d low of the square. What's below? I got that. And like I said, the top was u substitution. Now from there, simplify it. Multiply through, combine like terms, that kind of stuff. I'm going to end up with this: 9 times 9 minus x squared over x to the fourth. Okay, that's what I'm going to end up after I simplify down here. So I'm going to put some dots in there. All right, so we want to evaluate the value at that max point. Well, my max point is 3, 2, so I am worried about f prime of 3. Okay, so I can go ahead and plug that in. 9 times 9 minus 3 squared over x to the fourth. Can't even read my writing. Should be 3 to the fourth. Okay, on top, inside I'm going to have 3 squared is 9. 9 minus 9 is 0, isn't it? So I'm going to end up with 0 over 3 to the fourth. So my answer is just going to be 0. The value of that function, or the value of the derivative at that max point, would be 0.
How does that make sense?
Well, I'm glad you asked. All right, so look at the function over here. Okay, this is the function. So our derivative is going to be essentially the speed at that point, right? This would be, imagine something coming up, flattening off. Okay, so if something's coming up and flattening off before it's going to start coming back down, that's called a point of inflection. So it's almost like, you guys ever ride one of those, like the pirate ship? Like the big pirate ship amusement park ride? You know what I'm talking about? When you come up to the top, right, that moment where you just kind of freeze and your guts like flop over in your stomach, you know what I'm talking about? And you feel weightless for a second? That would be that point. Because you reach that max point. That's that slight moment where there is no upward thrust or downward thrust. All right? That would be that point right there. Does that make sense? Does that example make it sound a little smart sound? And at the same aspect, we're finding that point. You just don't have to get an upset stomach about it, It's perfect. Oh, same thing, All right, next one. We have a relative minimum here, okay? Now, this is f of x equals absolute value of x. It's a little tricky, okay? Anybody see a problem with this problem?
There's no derivative.
What's that?
Derivative is 1.
Okay, you can't really find the derivative, right? And the other issue is that point, okay? That's a sharp point. It's not a mathematical term, but that's a sharp point. That's two lines coming together like this. All right, it's making like making a corner. Excuse me. Every time you have that, it presents an issue. It's not a continuous function. Okay, something started, reset, and restarted. Okay, so if we would also look at this in the sake of limits, when we went back and talked about limits in pre-calc, if you look at the limits in both directions, it's going to go two different ways. Okay, so in that aspect, because f prime of x, when x equals 0, does not exist for two things. One, you can't find the derivative of it, and two, it's got a sharp point. All right, so that it's still a minimum. It's still the function minimum, but we cannot evaluate the derivative at that point. That's just kind of one of those weird ones. All right, last one, I have sine function. So this is f of x equals sine of x. This graph there on the left. Now, even though there's numbers, I have it graphed in the form of radians, okay? So this max point here would be pi over 2 and 1. And the minimum point down here would be 3 pi over 2, negative 1. All right? Now, again, looking at this graph here, this is kind of going to be like that first one, like the pirate ship or the roller coaster. At our max and min, what should our value be, probably?
0.
Should be 0, because that's one of those inflection points where we go from increasing to decreasing. All right, but let's check just to make sure. So f prime of x was going to be the cosine of x. Okay. Derivative of sine is cosine. So we need to check out 2 points. So I need to find f prime of pi over 2, and I need to find f prime of 3 pi over 2. All right. So then this is going to be the cosine of pi over 2. You remember? Do you guys remember what the cosine of pi over 2 is? 0. Over here, the cosine of 3 pi over 2. What do you think that's going to be? 0. Now, what are you guys just getting ready to say? Is it always going to be 0? No, not necessarily. Okay. All right, you guys with me so far? And where we're moving to is I gave you pictures, and I showed you where the min and max points were, right? We evaluated those points. We were working towards getting no picture. Okay? So then we have these things called critical numbers. Critical numbers let f be defined at c if f prime of c is 0, like we just talked about, or if f is not differentiable, then it's a critical number. Okay? Those are numbers we have to look at. Those are numbers we have to figure out what's going on at that point. And because it's a critical, it has to be a critical number for it to be a max or a min. Now, just because it's a critical number does not mean it's a min or max. It could be a local min, local max. But those every time it's a critical number, there's something going on. Okay. So, and we have theorem 3.2. Does relative extrema only occur at critical numbers, like we just said? Almost like I was ahead of myself. Relative minimum or relative max at x to c, then c is a critical number of f every time. Okay, again, your overall max and your overall min are going to be a critical number, have to be. Your local min, local max are also going to be critical numbers. So here's some guidelines for finding extrema on a closed interval. Find the extrema of a continuous function f on a closed interval from a to b. We're going to use the following steps. First thing, you want to find the critical numbers of f in AB. You want to evaluate f at each critical number in AB. You want to evaluate f at each endpoint, and the least. I bent my tongue. The least of these values is the minimum, and the greatest is going to be the maximum. All right, here we go. 3 big ones we're going to knock out. So for this one, we want to find the extrema of f of x equals 3x to the fourth minus 4x to the third on interval of -1, 2. Now, see if you can remember this or not. Back when you evaluated quadratics, how did we find our critical points there? So we did a quadratic. It was a negative quadratic. We had 3 critical points, 2 x-intercepts, and the vertex, right? If it was a positive quadratic, we had the same thing. Y-intercepts, vertex. But the x-intercepts were the toughest part to find, right? Do you remember how we found x-intercepts of a function? Plugged in a 0, or set it equal to 0, right? Set y-intercept you plugged in a 0, x-intercept you set it equal to 0. Remember doing that? That's coming back. Okay? So, we're going to find the extrema of the function. So, here's my function. It's going to be f of x equals 3x to the fourth minus 4x to the third. Now, in the same aspect, I need to find the derivative of this. 12x to the third minus 12x squared. That's our derivative. So we need to find out, whenever we were looking for x-intercepts, we had to find when x is equal to 0, right? And f of x is equal to 0. Now we're looking for critical points. We're finding out where there's critical points are happening, that there's inflection points, the points that make your stomach jump on the roller coaster. All right, so we want to find x values where f prime of x equals 0. So it's very similar to what we've done in the past. So we have f prime at x, which is 12x to the third minus 12x squared, we just found. We want to set that equal to 0. Now, can I factor that yet? Not pretty, but I can pull something out, right? I'm going to pull out 12x squared. So I have 12x squared I pulled out. That's going to leave me with x minus 1. That's equal to 0. All right. So from there, I set both of those equal to 0. If I set 12x squared equal to 0, what am I going to get? It's going to be 0. And then if I set x minus 1 equal to 0, what do I get? 1. So 0 and 1. Those are my two critical values. You all right with how I got those? Okay. So those are my critical values right there. Now, that gets me through step 1, 2, and that's just step 1. So step 2 and 3 I'm going to do all together. I like to make a little chart. Okay. How many critical values do I have? 2. I also have to evaluate the endpoints. Okay, because they kind of got chopped off. I mean, I'm just essentially taking a function. Lord knows what it's doing. It could be something like this. And then all of a sudden it's chopped to here and here. All right, so I have to evaluate those endpoints as well. Because here, look at this function. If I slice it here, that's going to be a local match, right? But is that an inflection point? No. So this point here could not equal 0. You with me? That makes sense. Because I chopped it off. If I don't include that inflection point where it changes value, it's not going to be 0. So that's why I have to evaluate my endpoints as well. So I have to take what I call my left endpoint. I have two critical numbers, critical values, CV, CV, and then my right endpoint. All right, so then I have to plug each value in. So I want to find f at -1. Okay? So I end up getting a 7 there. Now we're just plugging these back into the original equation, not the derivative. Okay? We use derivative to find the critical points. Now we're just plugging these values back into the original. So f at -1, if I put a -1 in up here, I'm going to get 7. Okay? If I find f at 0, which is my first critical value, put a 0 in back in the original, I get 0. F at 1, put it back in up here at the top. 3 times -1 to the fourth minus 4 times -1 to the third. Okay, this is going to be a positive 3. This is going to be a -4 and a -1. It's an odd, so it'll be 7. All right. Okay, 0 gave us 0. F at 1 would end up giving us -1. And F at 2 would give us 16. So those are the 4 points I just evaluated. Which one's the smallest number? -1. This is my minimum. What's the biggest number? Huh? It's at 2. That's 16. That's my max. Done. Kind of cool, wasn't it? That was fun. I enjoyed it. Yeah. So, that was the first one. Second one, let's do another one. So I want to find the extrema of f of x equals 2x minus 3x to the 2/3 power on the interval -1, 3. Right? I just want to be mean like that. So f of x equals our 2x to the minus 3x to the 2/3. F prime of x then is going to be 2 minus, would be 2x to the -1/3, right? Yeah, 2x to the -1/3, so that'd be 2 over x to the -1/3. So that gets me to there. So I got to be able to factor this. There's nothing to factor, is there? Looking at those two terms, not really. Let's write it as one fraction and see what happens. That might help us. So if I want to combine this, I'd have to multiply this guy by x to the 1/3 power, right, for a common denominator. That's going to give me 2x to the 1/3 minus 2 over x to the 1/3. I'm going to go ahead and factor a 2 out. It's the 1/3 minus 1 over x to the 1/3. Just not pretty, is it? Now, we go back to our days of, well, just remember, a 1/3 means a third root of something, correct? So what two things make that bottom 0? It's the other way to look at it. Because we look at what makes it 0 or what makes it does not exist. In this case, we got two numbers. For one, when x equals 0, the bottom's 0, right? That doesn't work. Kind of back to our domain and range days. So 0 would be a value that makes it 0. So that's when I just said it equal to 0. Second value would be a 1. Because if I put a 1 in here, cube root of 1 is still 1. 1 minus 1 is 0. Right? So that would be equal to 0. So that would be my two values. All right? Sometimes they don't always factor, so if they don't factor, you just kind of have to think through it. Domain and range type. There's my two critical values. These are my CVs. So now I have four things to evaluate. My left endpoint, my right endpoint, my two critical values. So left endpoint, critical value, right endpoint. All right, so f at -1. I put it, if I want to find f at -1, that is going to be -5. Plug it in. This is just straight calculator work here. F at 0 is going to be 0. F at 1 is going to be -1. And f at 3, that's going to be 0.24 is actually what that is. And it's a little bit ugly. All right, so what's my minimum value? It's at -1. My maximum value,
0.24 negative.
that's negative, yeah. So it's 0. There we go. Done. Questions? Anybody? This last one is,
Why is calculus after pre-calc? Pre-calc was so much harder.
we'll stop there. That